with the numbers, and everyone will have different numbers. Okay, good morning. What we're going to do today is the attendance sheet goes around, you're going to sign the attendance sheet. And I've got more buttons to push today. I have an additional set of buttons and things to play with. So we're going to play with some new things today. And I'm excited. A number of things. I guess if I read my notes, I know what I'm supposed to say. The first thing is we may have a few extra classes at the end here, which would be good because what I did last time when we did this is an opportunity for people to present projects that they're working on, and then we can all judge the statistical methods that they're using to see if we have suggestions. I was going to say to see if we should laugh at them, but that's not the point. One thing to think about of the projects that people are actually working on, where they're actually doing real things with real data, if you would consider presenting that in a class, and then we can go over how people have done the analysis, and that will show other people what you're doing with the data. And it also may provide opportunities for people, including me, to suggest alternative sort of analysis that might be useful. So this is just optional. There's no extra credit for this, because I never give extra credit for anything. But there are, you should consider doing this. So if you have projects that you would like for all of us to talk in a supportive way, despite what I said before, I'd be happy to do that. So it's something that you might think of. And I know a number of people are actually working on real projects. So you should start to prepare something that you could explain to everybody else. And it's also good practice in using devices like this and that. And this is not a nice device to use, actually, because when you write on these boards, it doesn't show up well. And I'm told a lot of the engineering people still can't deal with that, so they still write on those boards a lot. But actually, it shows up much better writing on these things. Right, thank you. These things, and this is my new switch, so I can do things like that. So we'll do that later. Thanks. So as I said, you should talk to me about that, and we'll do that maybe in a few weeks from now. Second comment is, in the original schedule, next week we have no class because since it's spring break, I guess everybody from Florida is up north somewhere. So I don't know how that works. But there'll be no class next Friday. And the Friday after that, it said that there would be no class. But it's not true. There will be a class on the 20th because I'm going to be flying back faster from Los Angeles than I thought. So I'm practicing earlier and faster. So I've been practicing. So I'll be back here in time for the 20th. So there will be a lecture on March 20th, which is, I guess, 2 weeks, right? 14 plus 6 is 20. Okay, what I'm going to do today is, first of all, go over the homework. And a number of people have helped make one of the points that I wanted to make in the homework by showing me that their programs produce different numbers than my program and different numbers that are in the book. So this is a useful thing to understand, that everybody's ANOVA seems to produce different things, which of course it shouldn't, but it seems to do that. So that's useful to know. Let's start off with the first problem, which was has a lot of these words in it. Basically, instead, too many words actually. The basic idea is that we have some sort of measurement. I have to do this in some order. So the first problem, basically we had a series of measurements. And we had one value which was special in some way. And that value was special because it was actually equal to the value from the data. And it was this parameter which we call h, which stands for Hurst, but it doesn't matter what it stands for. And that value had a value of 0.61. And then what we did is we did something magic to this data, we shuffled it, so we randomized the data. And that produced different values of h from the same data, which were 0.55, 0.56, 0.64, 0.54, 0.51, 0.63, 0.55, 0.48, 0.62, 0.55, 0.54, 0.51, 53, 54, going off the edge here. Okay. And the deal was that how likely is it if we do a comparison of this number each time with one of these numbers and ask which is bigger, if this number was really different than this number, let me backtrack a second. Basically, in the original data, there are correlations between values. And when we do the shuffling, it should remove the correlations. So we're trying to, that is, if the correlations were present and we shuffle them, we should get something different. And that seems like a nice way to make sure the correlations are really there. So every time we do this test, we compare this one to that one. If this number 0.6 was bigger than all 16 of these numbers, there's 16 of these, then we would think that it's very unlikely that that would happen just by chance, and therefore the fact that this is bigger than those would be statistically significant. And the argument that I implied here in the homework problem was that each time we do this test, we have a probability of a half that this will be bigger than that. So if we do this test 16 times, and if for all 16 times this was bigger than that, then the probability of that happening to chance would be 1/2 to the 16th, which is a small number, which is a number that's something like 1.5 times 10 to the minus 5th. So this is a nice statistical test because we can compare one thing to a number of other things, and if we do it often enough, and if it differs often enough, this is a nice way to establish statistical significance. Now, it turns out that there is something more subtle than I first thought going on here, and currently we use this statistical test in a paper that we're currently arguing with referees about. And one of the referees argued that the probability should not be 2 to the minus 16th, but 1/16. And I'm still actually trying to figure out whether the referee is right or not. At this point, we think the referee is not right because what we're doing this test each time is independent. So it's a half times a half times a half. But I'm still trying to deal with this issue. So I'm not as absolutely sure about this procedure as I was 2 weeks ago. But assuming that I'm right, this is how we're going to handle the problem. And I may be right, too, so it's not so far-fetched. What we actually have in doing this data comparison is this time, and this time, we got values in the shuffle data that were greater than 0.61. So one of the things we can calculate is given a binomial distribution of 16 things, what is the probability that 3 times out of that 16 we get something that's greater, given that each time the probability is a half? So this is really the probability for a total of n equals 16 of 3 successes, given that the probability is a half. That's what we're trying to calculate. So how do we calculate this? Well, we can calculate, what we're really asking is that the probability, we're looking for the tail of this distribution. And actually, we're looking for the other tail. I'll do it that way because then I'll be confused in my notes. So we'll do it this way. Another way to say the same thing is we're looking for the probability, again, of 16 things for really successes less than or equal to 3, where the probability is a half. So we have a distribution like this. So these are the number of successes, number of hits, which we're calling k. This is how often that happens, so this is the probability density function. And we're trying to see what's the probability of getting 3 or less hits in this. The probability at a half out of 16 would, of course, be 8. So
how does that differ from the first thing that you wrote, where you're looking at the other tail?
it doesn't differ in principle, but usually the way we would label these axes is that 8 would be here, and 0 would be here, and infinity would be over there. So we're really asking that we're getting less than 3 successes rather than greater than 15 successes. So just from the way the axis would be normally labeled, we're really dealing with the other tail. They are, of course, mirror symmetric, and if we picked the point that was equivalent over here, we would get the same answer for the area. But formally, from the way I'm setting it up, would be we should really pick the tail that we're interested. And we're interested in a one-tail distribution here. We could also ask for what's the probability of both of them. But we're just really asking what's the probability of getting 0 successes, 1, 2, or 3. So what we need to do is to add up the probabilities of each of these together. And the probability of one of them, of n equals 16, k with p equals a half, is equal to this expression of the number of combinations of k things taken from a group of n things times the probability raised to the kth power times 1 minus the probability raised to the kth power, where this expression is equal to n factorial over k factorial n minus k factorial. So what we just need to do, as many of you did in the homework, is just evaluate this expression for these 0, 1, 2, 3 terms. So we'll do that. So first of all, let's evaluate this, the probability for at k equals 0. So that's going to be 16 factorial over 16 factorial over 0 factorial, 1/2 raised to the 0, 1/2 raised to the 16. You can see in all these terms, this term is going to be the same. This is equal, actually, as I said before, times 1.5 times 10 to the minus 5th. The next one is the probability of one hit will be 16 factorial over 15 over 1 times 1/2 to the 1 times 1/2 to the 15. So again, you can see we're always getting here 1/2 to the 16 power. To evaluate this expression, 16 factorial is 16 times 15, etc. factorial divided by 15 divided by 1. So this cancels. So this is a factor of 16. So now this is 16 times 1.5 times 10 to the minus 5. And now the probability of 2 is going to be 16 factorial, 2 factorial 14 times this same 2 to the minus 16th. And so that's equal to 16 times 15 times 14 factorial over 2 times 14 factorial 2 to the minus 16th, or that's equal to 8 times 15 I did this right, 16 times 2 to the minus 16th. And that should be 120, which it is. So this is 120 times 2 to the minus 16th. And doing the same thing for 3, we get 16 over 3. 16 minus 3 is 13. So that's 16 times 15 times 14 times 13 factorial divided by 13 divided by 3 factorial. 3 factorial is actually 3 times 2, which is 6. So we can cancel out a 2 here to make this 8. We can cancel out a 3 here to make this 5 times 14 times 2 to the minus 16. And if we add these together, then we actually get 1 plus 16 plus 120 plus 560 times 2 to the minus 16. And this adds up, as some of you found, to 0.0106. So what is the conclusion? What is the conclusion here? Are the correlations present? Yes. So again, I mean, it's useful not to lose track of the tests that we're trying to do. The question we're asking is, are correlations present? And the way we're asking that is we're testing the null hypothesis that there was no difference between our h equals 0.61 and the shuffle data. And we found the probability of h1 being true is 0.01, so that's small. And so therefore h0 is not true. And therefore the h between the data and the shuffle data, which usually referred to as surrogates, are different, and therefore the correlations are present. Again, it's important to come to this final end for all of these problems, because what we're trying to do in these problems is provide information about the original data. So it's important to realize that we're doing these tests, and to remember what the conclusion is, to follow it all the way through, to state very explicitly what the meaning of those p-values are. Now, you can see that there are lots of different ways to calculate these coefficients. A number of hand calculators do them now. If you wanted tables of these coefficients, where would you look for them? What? Spiegel. No, they're not in Spiegel. That's not a bad guess. But they're probably in, I'm not sure, but they're probably in Abramowitz and Stiegel Handbook of Mathematical Functions, because everything you'd wanted to know about statistics is, or any tables of numbers is in there. So that would be a good place to look it up. Numerical Recipes actually has programs, because these are related to things called gamma functions, so you can push buttons on the machine and these can be calculated. And in fact, the way these are normally calculated, you can calculate them by expansion the way I've done here, so you can expand all these terms. But this is very inefficient, especially if you multiply all the numbers and try to cancel them. So there are approximations and other ways of generating these functions which are computationally more efficient than just doing it this way. And I have a program in BASIC that does the gamma functions like this. So there are more efficient ways of doing this. And again, this is this usual principle that very often the most straightforward way of computing something is not necessarily the one best computationally efficient. And there are asymptotic expansions of gamma functions that are better at doing these probability things and much faster. On my old hand calculator, my TI hand calculator, which goes up to 69 factorial, it's the longest calculation that can do. So you put it in, you have to wait a long time, and then the number pops out. And 69 factorial is about 10 to the 100th. So that's the biggest number that can do. So these factorials get very computationally big very fast. I think everyone handled this well. A couple people, more than one, tried to do this problem in another interesting way, which is not what I had in mind. What I really had in mind is this half, which is sometimes called a knife edge test, I think, because we're seeing whether the data at any one value is greater than or less than, in this case, the surrogate. What a few people tried to do is from the data determine what the average value was of those surrogates, the mean of the surrogate. And then from that, use the binomial distribution. It's not clear to me that's quite what you want to do. I need to think more about what that means, but I'm just saying that a number of people did that. As I said, I had in mind comparing these factors of a half. Since we're doing it 16 times, it's a half times a half times a half 16, or 1/2 to the 16. So I need to think more about what the implications of handling this the other way are.
Why do it this way
Oh, you could do a sign test too. I'm trying to remember if I did a sign test on this. Sometimes there are things in the notes here. In this case, I think a sign test would produce exactly the same result, because that's what the sign test is doing. It didn't. And that was a sign test that you did by using a canned program?
No, I did it by hand.
But in calculating the probability for the sign test, you're usually using, it should be a binomial, right?
Right. We may have used the probability from the mean rather than actually just using a plus or a minus.
Okay. Okay, that will produce a different result because you're dealing with the means, so that will change it. I didn't do any other tests on this data. Sometimes I do other tests. And as I said, there's still this issue whether it's 2 to the whether it really goes like 2 to the minus n if there's only one hit or 1 over n. I'm still dealing with that. Are there any other questions about this problem? I think people had a handle on this pretty well. The next problem was actually just the same problem I did in class, just in case if anyone actually wanted to do it themselves. So there's no real reason to repeat it. We had 2 different sets of numbers from 2 different experimental conditions, and you order them, and you're trying to find out whether the value of central tendency of this one is different from that one. And what we do is we place all of them in rank order, and then, so here they all are ordered, and then we can do the sums of the ranks, for example, of this one, which seems more reasonable than this one because there's fewer numbers. And the sums of the ranks in this case is 30. And then the statistical test tells us if this parameter 30 is greater than a certain value, which we look up in a table, then we could reject it. Now you can see we could have just as easily picked the other numbers to make the ranks. And so in this case, it will turn out that there are 2 limits, whether this number is too large or too small. And it turns out we need to deal with the other end of this distribution, and we can convert that by using this formula. So it turns out when we look it up in the table, or in my basic program, number 52 pops out. We need to convert it because it's really 28. We're only dealing with the other end. And the deal is this 30 is not less than 28, and so it's not statistically significant. If you use my basic program, what happens is that you put in a file of these numbers and of those numbers, and the program cranks actually for some time and produces that the p-value is 0.127. So you don't have to look things up in tables, because I don't like to look things up in tables, because then I might be tempted to interpolate and I'll do it wrong or not carefully, and so I don't want to do that. So it actually produces the correct p-value. And these have all odd values because they depend in a discrete way. So this was just a repeat of the problem in and as I said, this is in the book Hollander and Wolf, which is this excellent book in doing non-parametric statistics that I recommend if you're want to try some non-parametric statistics. Are there any questions on this procedure? Okay, and this example is also worked out in the book. The reason why I assign this problem is I've used this problem a lot, actually, in making sure that my program works and in testing the program. So I make sure that I put in these numbers and got the same numbers that they had and reproduced the values in the table and some other things. So I found this a nice test problem to make sure the program I wrote was working, and also found out that other programs don't work. One of the lessons we're going to come away today, I hope, from with wherever those prepositions are in the right order, is computer programs that do statistics don't always give the correct p-values. This is really pretty amazing if you think about it. Right? Because usually people use these programs because they have no idea what they're doing. And so they put the data in the program, and a p-value comes out at the end. It goes, p-value comes out. And so this is really pretty scary. Now, there are lots of reasons why this happens, some of which are quite subtle. One of the reasons why this happens is, so far, I don't know of a case, actually, of a program that does this just because the program is wrong. So there may be programs that are just bad. But in the case where I've seen it, I haven't seen that happen yet. Although someone has an F value here from the homework that just looks wrong to me. So they could have entered the data wrong, and the program could have really done something wrong. But there are two other reasons this happens. The first one is we really have some decisions to make in handling some tests. And those decisions could be made different ways. And we saw this last week, for example, in terms of the ANOVAs, where how we want to handle the interaction variances and how we normalize them with respect to the total or with respect to just the between variances between the columns and things like that. So the different tests can actually be done in different ways, and that's one reason why different programs produce different results. The second reason, and this is more subtle, is some programs take shortcuts in computing the p-values. And sometimes those shortcuts don't work. And the case that I've seen in one program is I've shown you for these non-parametric tests that actually computing the p-values is actually a little bit hard. That's why there are tables of this, because it's a pain in the neck for your program to compute it, and because people made tables before computers were easily available. And it's storing, like Hollander and Wolf probably has about 30 pages of tables in the back. And storing all that data in a small computer program on one disk is actually not so easy. And then you have to have a routine that finds the right value in the table. And people aren't used to programming like that. People use tables in programming, but it's sort of like a last resort. People don't like to do things like that. And so one way to get around this is to use certain approximations to calculate the p-values. And we saw specifically in the non-parametric test there are certain approximations, but these fail when the number in the data is small. And that's exactly the case you want to use the non-parametric tests. And so since they use these asymptotic formulas, they get the wrong p-values. And I know what's going on because I know the asymptotic formula, and I can compare them to what the program produced, and I can see the program has produced the asymptotic formula, but not the correct p-value. And usually the difference, if n is small, like around 5 or 10, we're talking about an error of approximately 2 in the p-values. Okay? So this is another reason why the programs are not always right. And the third reason is maybe some of the programs are just wrong, although I haven't seen examples of that yet. So I think when I use one of these programs, what I like to do, and I recommend that you do this, you probably won't, but I recommend it. So this is my recommendation, is before using one of these programs, what I would do is take known data, I guess data is always known, from, for example, from Spiegel, where the result is calculated, put it into the program, and determine the p-value, and see if that matches the p-value that Spiegel calculated, for example. And I do this all the time. In fact, I have the set of data on heights and weights, or heights of fathers and heights of sons, that I use to check programs on correlations and R values all the time. And I use it to check my programs and other people's programs. And it gives you an idea of how accurate the program is. And that's a very simple one. But I use the data I just showed you from the non-parametric test to test the non-parametric programs. And I do this all the time. And I think it's really worth doing. And it's especially worth doing on some of these ANOVAs, because we're going to see that we have at least 4 different values from people in the class and me in the book on the p-values for the ANOVAs. And that has to do with each program handling things differently. So it's good to know what your program does. So it's good, especially in terms of the ANOVA, to take the last problem that I assigned, which was 1613, and plug it into your ANOVA program, and see if it matches Spiegel. Now, it's not necessarily bad if it differs from Spiegel. My program does, but at least you know what the program is doing. You should know what your programs are doing. So that's worth stating. You should know what your program is doing. Okay. And I just, as I said, I want to emphasize this because these p-values are black boxes to a lot of people. And it doesn't make any sense, as I said, the way a lot of people do is to try to run 3 more experiments to get the p-value less than 0.05 if there's a factor of 2 wrong in the p-value. Okay, so if that isn't hit once every half hour, it'll crash. There's some mystical thing that goes on with that computer. I'm serious, too. It's not. So I think this is really important. I don't think people fully understand this. I'm really emphasizing this. I think as a working scientist, it's good for you to put data into your program and really understand what it's doing. So this is a very practical suggestion. Having said that, let me do the homework problems from Spiegel. The first problem was 16.7. And here we have something called A, which are wheat grown in particular type of soil, treated with chemicals A, B, and C. And we have, so this is going to be a one-way ANOVA. We have just treatment A, B, and C, so we can forget about that other one. We have just a one-way ANOVA. We have 4 numbers in each row, and we're trying to see if this is different from that, is different from this. And since Spiegel goes through the calculation, since you can read as well as I can, since I seem a little off today, maybe even better than the way I'm doing today, I'm not going to go through here. But what I thought I would show you is what came out of my computer output on this to just give you a sense how my program worked, and everyone's program works a little bit different. This is from a program on the Macintosh that is no longer supported, actually, although it still runs. I think it was originally from operating system 3, and it runs on operating system 8, so it's very well written. It didn't take any shortcuts. It's called StatWorks from Cricket Graph. If anyone wants this program, I can give it to them since it's no longer supported. It's not even illegal to trade it. It's actually a very nice program. Except actually, now that I say it, I don't think it works on System 8. I think it worked up to System 7. It may have just stopped working. But I have a Mac Plus at home when things get really desperate. So, okay. In this program, what you needed to do, and this just gives you a feel for how different programs handle data, is this is the data that we put in, and I have to specify a category. So I specified 1, 2, and 3 to define the categories, which I guess I could have done A, B, and C, but I just happened to do 1, 2, and 3. And then I could put the numbers in that correspond to that category. And this is the tabular form that I need to put it in for this particular program. So this is treatment A, the numbers from that, treatment B, and treatment C. And all I needed to do was to put in the consistent label. And then this program produced an output that looks like this. I guess when we get into high definition TV, then this won't be a problem. I was going to do it like this, it doesn't work like that. So here we have the between variance, the within variance, and the total variance. The sums of the squares was 8. The within variance was 6. You can see the between variance is greater than the within variance. We have 3 minus 1 degrees of freedom here, and n minus 1 times n minus 1 degrees of freedom, which is 6 here, which is 9, 3 times 3. The mean squares worked out to be 4.67. The F ratio of this is 6, and it turns out that the probability here is then 0.02. So the difference between these treatments in this one-way ANOVA is significant at the 0.05 level, but is not significant at the 0.01 level. So this was a nice intermediate case. And we can see that from the numbers. that these things kind of look different, but not strikingly different. So maybe it is, maybe it isn't. And that's what comes out of this test. Actually, it looks sort of similar now that I look at it. So maybe these are all higher than that, but not and a little bit higher than this. So you can see there might be something here, but might not be. Now, I've also done another non-parametric test on this called a Crustal-Wallace test. And in that case, I calculated a p-value of 0.04. And again, this is what I've been saying all along. This is a typical case. We have a small number of values. We have 4 numbers at each of 3 conditions. This would be a typical case where a non-parametric test would be more appropriate. And you can see that the difference in the p-value between the parametric test, the f-test, and this ANOVA differs from the non-parametric test by a factor of 2. And this is what I've been saying all along. So again, people are very much into believing these p-values too rigorously. And how we do the test produces different p-values. So which tests we do and how well the data matches the assumptions, usually the fact that it's Gaussian, can easily change p-values by a factor of 2. Now, for better or worse, I sort of know, as we've seen when I gave the same data done with a number of different tests, that I know which tests are likely to be more statistically significant for different types of data. So I can look at the data and choose a test that will be the most statistically significant. And this is fair, because I really know how the tests work. And it's a little bit unfair in a way that I could probably always look at data and find more statistical significance than you thought you had in your data. But maybe it's good. Maybe you should know someone like me. So, but again, I'm trying to give you a feel for this, because as I said, people get too focused on these exact values without getting a sense that the assumptions in the test can differ. And this factor of 2 difference is typical of the difference between a parametric and a non-parametric test. If the data is not, and it can work either way, these values can be bigger or smaller. If the data doesn't look like there's anything really going on, then usually the parametric test will be too good. And as I said, in just looking at the data, it doesn't look like anything is really going on. And in that case, this parametric test will underestimate, will be too statistically significant. On the other hand, if there's something really going on, but there's a lot of variation, then the situation will be reversed. So maybe this is worth writing down. This is a general rule of thumb, which I think is right. I won't bet my life on this, but I think is right. So if nothing is really going on in the data, that is, if H0 is really true, and typically the p-value from the parametric test, like the ANOVA, for example, gotta feed it? Is it better now? That was a virtual animal.
Can I bring my pets?
For the what?
Can I bring my pets too?
Virtual pets. Virtual pets are loud. I don't know about real pets.
They'll be quieter, I swear.
Not if I bring mine.
Yeah.
Somehow, sort of just looking at a classroom of like vicious dogs sitting in every other seat looking at me sounds like sort of a frightening.
Vicious.
And then after that, I pictured a scene from 101 Dalmatians. But okay. Now let's see if I drawn this right. Yeah, this is actually right. Typically, if there's nothing really going on in the data, the parametric p will be less than the non-parametric. On the other hand, if H0 is really false, so that there really is an effect, but there's lots of variability, so that the data is not Gaussian, then in this situation, typically the parametric probability will be greater than the non-parametric. And I would say from my experience, this is a rule of thumb that I found to be true. And I don't think I could give them, this second one over here, I can give strong justification for. So I put 2 checks on this one. This is something that I found, but I could prove less, I can give less justification for. So this gives you some sense of the variation of p-value. And this is what we just found. The case we were just dealing with is this first case where the parametric was less, that is more significant than non-parametric. And the case I gave in the data set where I used about 7 different tests to analyze the data was in the second case. It was non-Gaussian. We found that the non-parametric was less than the parametric. That is, the parametric were bigger. And in this, that was the case for that data set. All right, so now let me do the second ANOVA problem. And in the second ANOVA problem we had machines and shifts for the machine. I think it's this one. So we have now a 2-way ANOVA. We have machine A being used on Monday, Tuesday, Wednesday, Thursday, Friday. I guess the machine gets the weekend off. And machine A, B, C, and D. And we have also the second variable running this way. And in this case, we actually had 3-way ANOVA because we have the first shift and the second shift. And what I found from this, is this the right table actually for this 16?
Yes.
Okay. I created a file in order to handle this. The file looks like this. This looks awful like a 2-way ANOVA. So maybe I didn't, right. So we have addition data from the shifts. And so I have the machine number and the day of the week. And this repeats twice because I have the 2 shifts compressed here. And so this was the data file that I put in. And these were the results that I got out of this. Maybe because I didn't put in the shift business, maybe that's where I got results that were different from the book. But in this case, these were the results that I got. So if this is the first columns, column 1 was between the different machines. These values are the same values that are in the book. And the numbers here are all a little bit different, but I got the fact that, yes, there's a statistical significance between the machines. Then when I looked between the days of the week, what I found was no, yeah.
That's what the problem is, because the question wasn't about the days of the week, it was the shifts.
The shifts, okay, so I did the wrong.
Days of the week was just to give like extra.
Okay, so then I did that wrong, okay. So that's good to know, maybe that's why some of my numbers are different, okay. In this case, I got that there was no effect of the days of the week. And the third thing was to test for interactions, and between these 2 variables, I found there were no interactions. So again, this is the main principle in what I was saying last time about what we're looking for. We're looking for main effect, and then interaction, in the sense in which I described main effects and interactions last time. Okay, I guess I should read the problems better. And everyone has slightly different numbers here, so it wasn't just me, but everyone has slightly different numbers from different programs. So exactly what these programs are doing may have, again, since we can normalize these things in different ways, to give different results. And so I think, again, before using an ANOVA, you should really test it with some data, whatever program you're going to use. The purpose of this was to just have you do one of these so that if you're working for someone or decide for yourself, you suddenly want to do not suddenly, but we want to do an ANOVA, then you know how to go about doing it. And at least you recognize there are these possible problems in it. Are there any questions on anything we've done so far in all these statistical tests? Because now what we've done so far is we've started off by discussing Gaussian statistics involving parametric distributions, and then we've discussed non-Gaussian distributions where we use non-parametric tests. And now we're going to do something different. We're going to do something even more general, where moments like the mean and the variance don't exist. So we're about to get into a whole new area. So are there any questions on where we've come so far? Okay. You had a chance, you can always take up that chance later, so it's not irrevocable. Let me try to give some background to this and try to elaborate a little bit more on this. In analyzing data, we're always making certain assumptions about the data. And as I discussed in terms of the paradigms, these assumptions are made so often and so deeply that very often we don't even see or realize what assumptions we've made. We do if we really need to prove the theorems of how these statistical tests work, but even there the assumptions come and go so fast that we're so used to seeing them or just assume them by granted that we don't really realize the assumptions that have gone in or how important they are or ever check to see whether the data meets those assumptions. And we've seen this in a number of cases already. We've seen this, for example, in the use of least squares in order to fit some function like a straight line to data. An example is fit of y on x. And we've seen that this works or is valid or is the best line only if these errors, these deviations from the line, have a Gaussian distribution. Now, how often do we check that those errors, which are called the residuals, have such a Gaussian distribution? And the answer is basically never. Okay. So again, we're using a method that makes certain assumptions about the data that in principle we could check, and maybe we should check every time, but nobody ever does it. And this is what I mean about just assuming that everything is okay because we're used to doing that. And we've seen, first of all, that we can get into trouble with these sort of things because sometimes distributions are not Gaussian, and so that this procedure is not a valid one. The case that I illustrate is when we have one data point that's way off, and that data point biases the least squares in a way that's far too strong, and it's happening because the distribution is not Gaussian. Now we have to deal, as we generalize through these things, we're now going to deal with a set of data which has, what I've been doing in the course is dealing with data that has less and less restrictive assumptions. So for example, in terms of the Gaussian, we first of all assume things were Gaussian, and then we relax that. We said things don't have to be Gaussian. But now we're going to relax something else. And the assumption we're going to relax now, it's hard to say it's a single assumption, but we're going to say that the moments of the distribution do not need to exist. Now, what does this mean? And this is really something very essential and gets to something that is always assumed in handling data for which may not be true in handling lots of data. I said that at one point, why we measure things more than once was somehow we had this idea that we would have errors that would cancel. And so, for example, the mean would be better in any one measurement. And again, this is essential in how we handle experimental data. This is absolutely essential and the underlying reason for why we do multiple experiments and then average the results together. Now, this is based on assumptions. And it's based on a number of assumptions. It's based on the assumption that the probability density functions exist. It's based on the assumption of a theorem which is called the central limit theorem. Central limit theorem in some ways goes back a very long while. Actually, one of the first proofs of the central limit theorem was a guy whose name I use very often, which was Markov. The proof was extended and more generalized by another guy whose name you may have heard of, who has different spellings, but Liebovitch. Liebovitch added the use of what are called characteristic functions, which I haven't discussed in the course, in order to extend the proof and more generalize it for the central limit theorem. This pissed off Markov, who was sort of one generation older, because this was his big deal, and Liebovitch had expanded it in ways that Markov hadn't been able to do. Both of these guys and one or two generations after them come from a famous set of very rigorous generation of mathematicians in St. Petersburg in Russia. What's not usually understood, the central limit theorem says a number of things. It's related to something else called the law of large numbers, which goes back again, of course, to one of the Bernoullis and some other people. Let me say something about the law of large numbers. This is sometimes considered one of the assumptions of underlying statistics. Can say this in a number of different ways. We have an idea that if we take something like a die, half a dice, and we flip it, if it's got 6 faces and it's fair, that 1 out of 6 times it will land on each face. Or if we flip a coin, we figure that a half of the times it will wind up heads, and a half of the times it will wind up tails. Now, it turns out you can't prove this. This is really an assumption, a postulate. In some parts of probability theory. In other parts, we sort of use this thing called the law of averages or the law of large numbers. I think that's what this is called. That if we do things often enough, we get kind of the result we expect. So if this thing is really fair and we flip it 1,000,000 times, then half of those times it comes up heads. Now, the central limit theorem is kind of a generalization of this. It basically says, it tells us that the mean will differ from this value of a half by less than a certain amount when certain conditions are met, and we can calculate what this amount is. And this is one of the ideas of the central limit theorem. And you can see why it's called the central limit theorem, because we're approaching the limit that we expect if we have the number of cases large enough. So first of all, this is intuitive, but it's also based on certain assumptions and certain theorems. Now, these theorems have certain assumptions, and those assumptions aren't true for lots of real data. One of the crucial assumptions that's involved in the central limit theorem, and this theorem also says that if we accumulate enough data that it will look like a Gaussian. One of the central assumptions here is that the second moment the variance is finite. And what we're now going to deal with are distributions that have two properties. The two properties are, first of all, the means don't exist. And second of all, things like the variance don't exist. So this means that this underlying idea required for the proof of the central limit theorem, in all of the versions of the central limit theorem, that the variance be finite and exist, is no longer true, and the central limit theorem does no longer apply. Which means as we go to more data, we're not guaranteed that the mean reaches a finite value, and we're not guaranteed that the distribution approximates that of a Gaussian. So this means that since the central limit theorem fails, or the assumptions of the central limit theorem are not satisfied, it means that the mean does not approach a finite limiting value. And it means that the distribution, the PDF, as more data is collected, doesn't reach a Gaussian. Even for the non-parametric statistics, we assume as we accumulate enough data, we'll get to be a Gaussian. That's called an asymptotically Gaussian. Asymptotically is the number of data goes to infinity. And now this is no longer true. Well, how can this be? I mean, this is very, very odd. Because we can always calculate the mean, right? Like if I do 5 measurements, and the measurements produce values of 1, 2, 3.5, and 1.1. I can always add these together and divide by 1, 2, 3, 4. And that should give me the mean, right? So how can the mean not exist? Well, this is not what we mean by the mean. In order for, this is technically what we call the sample mean. That is, it's a mean of the sample of data. What we mean for the mean to exist is that what we call the population mean, which is the real mean of the data exists. Now here, if we accumulate more data, we'll get a slightly different value for the mean. So what we really expect is that as we accumulate more data, these sample means may fluctuate, but eventually they reach a finite limiting value, that we then identify this value here as the population mean. This is something we almost never do in data. We never take more and more data and see what value the mean approaches. And again, the central limit theorem says if other conditions are met, what's the range of values that we can expect, which is really the variance and the standard error of the mean. Okay. So now this is the true meaning of what it means for the mean to exist. That it's not just doing this. That's not the mean. We must meet the mathematical criteria that this happens. And similarly for the standard deviation. The standard deviation should fluctuate but reach some finite value. Well, how can this not happen? Right? This seems pretty obvious, so we accumulate more data. And the answer, it cannot happen if we're in the following situation. Let's say we have a few big things, and I'll represent these values as the diameters of circles, just to give them some reality. So the value is proportional to the diameter. We can have a few big things. We can have many medium-sized things. And we can have a huge number of small things, small values. And when we have a situation like this, as we accumulate more and more data, the value of the mean, for example, 2 things can happen. Either the contribution of the large number of small values keeps driving the mean to 0, or the few big values that we have drive the mean ever larger. So in this case, there's no average size for things. And in fact, that's what's going on here in this room. There's no average size for the things in this room, as I've mentioned before. If I look around this room, there are about 100 things, maybe 50 things that are the size of a meter. If I look at the bacteria in this room at the size of a micron, there are millions of bacteria in this room on you and on me and the floor and the air. If I look at the size of a few angstroms, there are probably viruses and other particles in the size of this room that are billions and billions, as Carl would say. So the point is that many times in real biological situations and in physical situations, we have this sort of distribution of things that has properties that the probability density function doesn't exist, that these moments don't exist, and the word that I'm going to use to call things like this is fractals. So now we're going to deal with the statistical properties of what I'm calling fractals. And as I said, the reason why I'm doing this is because, and I'm going to emphasize fractals as systems in space or time that have these statistical properties. So these could be either objects in space or sets of values like numbers from an experiment, or it could be fluctuations like time series of values. So I'm not so much thinking in terms of fractals necessarily as objects, but in terms of sets of numbers that could represent or do represent data coming out of an experiment. Now I could use different words instead of this word fractal. Another word I could use to describe distributions like this, and this is the word that I'm blocking on the author of the book, but it's a very famous 2-volume series of probability books. Another word to describe these distributions is to call them stable probability density functions. And a French mathematician, Liebovitch, worked on these in the 1920s, and sometimes these are known as Liebovitch stable distributions. This is a phrase that Mandelbrot likes to use, for example, in his book on French. And these have certain properties, which I'm probably not going to talk about, that define them. Now, these stable distributions include as a subset, did you lose your pen or something, or you're falling apart, so maybe you should have left. You okay?
Yeah.
What?
I don't even know.
All right. Within the more general category of stable distributions also includes Gaussian distributions. So what I'm talking about now is not something that's different than Gauss. This is a set diagram. Looks like two badly drawn circles, but it's not. It's really a set diagram. Right, like from kindergarten when you had the Venn diagrams and things like that. If you ever, maybe not kindergarten, but soon after that, these were in for a while. They're still in. This is the sort of stuff that's competing with calculus. Remember I said there's discrete mathematics that competes with calculus. This is from that stuff. So these stable distributions include Gaussian distributions. So what I'm going to talk about is not different than Gaussian, but is a more general thing that includes Gaussian distributions as a subset. The Gaussian distributions have mean and variances that are finite, and we're going to see that stable distributions include mean and variances that are either 0 or infinite, which is another way of saying they don't exist. So when I say that the mean and variance doesn't exist, what I'm really saying is that they don't reach limits, they don't have limiting values, and they don't have finite values, or non-zero finite values. So that's what I mean when the mean and variance don't exist. Now, in a certain sense, a lot of the Gaussian stuff, though not all of it, really arises from really more linear approaches to things. That is, we think we can just add things together. In a certain sense, the fractals really represent more non-linear things, where we can't add things together. It's not as simple as this. That things interact with each other in a more complicated way. This is not completely true, but there's a flavor in which the fractals are related to more nonlinear phenomena than in terms of the linear analysis. And remember, the whole basis of the ANOVA, for example, was based on linear analysis of main effects and interactions. And now we're really closer to a nonlinear world where we don't really want to think of things as main effects or interactions. So that's going to be the fractals. Now, what I'm going to do, besides the fact I teach a whole course on fractals, which many of you have taken, but not all of you, and of which there are also tapes in the library. What I'm also going to do after we do the fractals is do what's called chaos. And I'll mention this now because chaos is one way of not doing ANOVAs. If the ANOVA tries to separate things into pieces that we evaluate separately, then some of the chaos analysis can evaluate everything all together. And it allows us to reach at different things, It allows us to reach at different properties of the system in a global way instead of trying to cut it up into smaller and smaller pieces. And we'll see that the chaos, therefore, also provides a different nonlinear approach to the A nova. So what I'm going to do for the next few lectures is give an overview first of fractals and then of chaos. So this is something I'm going to give in a few lectures here, what I do in the entire class, the entire other class. But what I want you to come away from this is some overall understanding of what fractals are and some of the properties. So I'll go through the properties overall, again, really aiming at these statistical properties and give you a feel of what's involved in that. And we'll start that at 10:30.